Which office?
Whatever opposite is in.
Okay, I'll mention something about it. Yeah. Okay, so let's start. A couple of things before we begin. Sounds like you can hear me at the back, right? I can hear you too. So, okay. So a couple of comments. One, homework 2 is due today. I'm hoping everyone is almost done. Okay. We are going questions. Questions about homework 2. I think it's of interest to everyone. Yeah. What does it mean that the information gain is 0? Yeah, but what does it mean that the information gain is 0? When do you get that the information gain is 0? Yeah. But specifically, you can look at the entropy that you get, and you basically know what the answer is, right? You don't?
So we can say for
How did you get 0 then in the information gain?
it wasn't the entropy.
But that means that the split that you had before and the split that you have now are the same. Something is wrong here, no? Look at the splits that you get. I think that means that you know. I think that that's what it means. But either way, I think it makes sense that you want to stop now, but check again to make sure that you don't know what the label is in this case. And that's even in the case where you don't know what the label is. To look at the example, but basically, what would you do? I mean, so basically, for all attributes, you get the same information gain. Which means you don't want to grow the tree anymore because you don't gain anything.
And you just pick them
Will you have a majority or it will be equal?
No, it's a majority.
Yeah, you can choose by majority then. Yeah. So this pertains to the first problem.
Yes, for the first one.
Okay. The question is when we define depth, do we count the root or not? How did we define depth, Brian? Did we count the root or not? The root is 0, okay. Okay, so that should be, I think, depth 1. So we don't count the root.
But in the code that's provided, right?
That counts 2.
If you put it 0, it creates such a tree.
Okay, so again, this is really not. You define it. You can use the definition from the code, or you can use your definition here. It really doesn't matter as long as it's clear what it is. So clearly, with a consistent definition, 3 is less than 4. And the question is, do you start with 0 or with 1? Typically, people start with 0. If you start with 1 and you do everything consistently, it's as good. Okay, 2 other comments. One is, question?
Yeah. For the homework,
I ask you to use the t-test in order to do that. So use the t-test to do this. Where was I? Okay. So 2 issues that we had some technical problem last time, and I wanted to make sure that it's okay now. Compass is free. Everyone should be able to access Compass again. Now, I realized that a few of the students that are in the process of getting registered into the class still did not get access to Compass. These students should just mail the TAs the same PDF that otherwise they would have uploaded to Compass, and do it at the same time that, or earlier, that they should have otherwise uploaded to Compass. I'm not sure why it takes so long, but it might depend on your host department, or not sure. Okay, so anyhow, so if you're registered, we know that you're registered, even though officially it's not there yet, and just mail it. There's nothing else we can do. And the videos are working now. I don't know if people have tried, but I think it should work. Oh, and the final thing, we are going to release the next problem set only on Friday, end of Friday, so you have a breathing room. Okay, and I'm going to talk about it next Tuesday. I just want to use this as a starting point for what I'm going to talk about today. So what we did last time was we talked about comparison between algorithms, and what you will do in the next problem set is actually run these comparisons between algorithms and hopefully see graphs that are nice as this one or almost as this one. Okay, so we talked about comparison between algorithms and then started to talk about this problem. So this is a slide that I showed at the beginning of the semester where we said, you know, sometimes we have data with blue and red points, and they are not linearly separable in one dimension, but if, as you can see, but if we add a dimension, then they become linearly separable. And basically what we started to do last time is to talk about mechanisms to do it. So one easy mechanism to do it, which is shown here, is explicitly invent more expressive features that are function of your original information sources. And today we're going to talk about other ways of doing it and facilitating this linear separation using the notion of a kernel. Oh, here's another example for the same thing. So you have blue points and grid points, and they're not linearly separable, right? So you would easily tell that this is the functional, the target function here. But if you manage to add features that are quadratic, so instead of using this feature vector, you transform to this feature vector, now it's linearly separable. And this is the kind of things that we want to be able to do. Okay, so we started talking about it last time, and we introduced the key terminology, really 2 concepts. One of them is that of a dual representation, and the second one is that of a kernel, and along with it, the kernel trick. So I'm just going to run through quickly what we did last time. we started by talking about dual representation. So this is our perceptron, or these are linear functions, right? And we said, notice that we can actually write the same function as a function. Here it's written in the weight space, and we can write the same function instead of using weights, using the examples that we've seen in the past. Or specifically, since we're talking about perceptron, those examples that actually matter for determining the weights, those examples on which we've made mistakes. So basically, this is what we call the dual representation. And then we ran through some algebra, and we said, OK, really what we want is we want to expand the feature space, right? We don't want to just work with our original xi's. So let's expand the feature space and move to a huge feature space where our features are really monomials or conjunctions over the original feature spaces, OK? So instead of xi of x, I'm moving to ti of x, where ti's are my monomials. And in exactly the same way, if you do some algebra, you can say, OK, this linear function, here, the linear function, its dimensionality is the number of monomials, right? The number of features that we have, right? This is the number of w's that we have here. And after doing some algebra, which I will not go over now, we realize that we can actually write it in a different way. This way. We can write it now. These are two equivalent ways, where the sum here is over the examples. And the internal sum is basically a dot product. It's a dot product in this huge dimensional space, but we can compactly write it this way, and we're kind of hiding any memory of the features. All we have is a sum over examples, provided, of course, that we know how to compute this guy, the k of xz. But this is the dual representation. So we move from this representation, which is the primal representation, and it depends on the dimensionality, to the dual representation that depends on the examples. And the question for us is going to be, why does it give us anything? And so we stopped when we said, OK, when we addressed this question, why does it give us anything? And the key thing was that we said that k of xz can be measured in the original space without really explicitly writing this T representation. So even though it represents a dot product, I don't really need to blow up the feature space and compute the dot product in order to compute k of xz. And we ended last time by giving this example, right? So we used this specific example of all three n monomials, and we said, you know what, this dot product can be computed if you just give me x and z. I don't need to know t of x and t of z. Questions on that? OK, so we gave a proof that, and we kind of hand-waved around this example, that this dot product can be computed just as this function. OK? And I left here another example that you can play with yourself. Hopefully you have played with it yourself, just to make sure that you understand this magic trick here, right? The fact that you can compute something in a 3 to the n dimensional space without actually touching the 3 to the n dimensional space, just by staying with the n dimensional space. Yeah?
So we rely on certain structure in a hypothesis space to be able to use kernels? Is that always going to be?
So far we are relying on the specific definition of the features that I invented, right? So I invented features which are monomials, and because they are monomials, I can compute it this way as 2 to the same. Had I invented a different function, the computation will be different. And you can think, and I'm going to give several examples later today, but you can try for yourself to invent, for example, take only conjunction of size 3 rather than all conjunctions over n variables, and you will see that you can also do it. You can figure out a concise function, but it will not be this function. It will be another function. Okay, so we are really relying on what is the new feature space. We start with a feature space, x. We move to phi of x. And this phi determines how we compute, what's the concise way to compute this dot product. Different phis, different concise way. And let's go over some examples. So before that, I just want to say, what did we get at the end? We got a different implementation for perceptron, which is called the dual perceptron. And this is what we do. We simply run perceptron, just as before. Instead of maintaining weights, what we are maintaining is the set M. Right? So we moved from a weight space to an example space. This allows us to know S of z. Right? S of z is just an indicator function, tells us whether we made a positive or a negative mistake here. And just by remembering the set M, we can later on compute this K. This is the dual representation. Yeah? Okay, we'll get to this question. Right? So clearly there's a trade-off here between weight space and memory space. And the intuition, of course, is if you have a small number of examples, do this. If you have a huge number of examples, maybe don't do it. And we'll quantify it. Okay, so I want to go over a few other examples to illustrate this notion. So we'll start with something that is called polynomial kernel. So again, what is the story, right? The story is that we can make predictions with respect to a separating hyperplane, irrespective of which algorithm we're going to use at this point, as a function of dot products in the feature space, right? We know that already. Now, we want to define this dot product in a very high-dimensional space because that gives us expressivity. Okay? So, for example, if I have these two examples, x and y here, I want to move to a high-dimensional space. In this case, I'm going to just move to a quadratic space. Okay? So instead of x1 to xn, now I'm going to have all the products until quadratic, which means I have 0th order, I have the first order, and then I have all the quadratic terms. Okay? So x1 square, x2 square, xn square, x1, x2, x1, x3, x1, x17, xn minus 1, xn. Okay? Same thing for y. And my goal is to compute this dot product. If I know how to compute the dot product, I know how to write my perceptron or my linear function. And this is going to take us time. That is a function of how long this is. And in this case, it's about n squared. Instead, what we said, I can go to the original space, the n-dimensional space, and compute something that we call k, and it's going to be this. Just compute the dot product in the original space plus 1 takes square. The theorem is that these are the same. This is the Kernel Trick theorem. Whether you compute A, which we showed is what we want to compute, or you compute B, which is via the trick, it's the same thing. Really, I'm cheating a little bit because for this to be equal, I should have put square root of 2 next to each one of these mixed terms. I'll show an example if you don't see it immediately. But really, these constants do not matter because at the end, I'm going to use this as my feature-based representations of the example, and I'm going to learn weights. So whether I start with initializing with square root or 2 or not doesn't really matter in practice. But for this to be true, I should have added the square root. So that's the game we're playing here. Is the game clear? Yeah. Just I'll do the math in a second, but you can do it yourself. I'll do it in a slightly different example. Just take this dot product, do the square, and you will get this. Okay, so this is another way of saying the same thing that I said before. I know that sometimes people get confused, so I'm saying everything 3 ways. But basically our goal is to work with degree 2 polynomials. Because this is our understanding of the problem. It's kind of this green and blue points in a circle that I showed before. But we want to actually work in an n dimension. So can we use any kernel that we choose? Not really. We said that a function k of xz is a kernel if it corresponds to an inner product, dot product, in some feature space. For example, let's assume you tell me, I know that I need quadratics, because what you have in mind is this picture. Okay? I need quadratics. So you want to use this as your feature, as your k, the dot product of x and z squared. Is it good or not? The answer is yes, it's good, because I'm going to show you that it does correspond to a dot product. Let's do the math. So I'm doing it for 2 dimensions. So I have x1, x2, z1, z2. That's enough. You know algebra, so you can write it also in 7 dimensions if you want. What is the kernel? The kernel is x1, z1 plus x2, z2 square. All right, that's what I've written here. Notice that it's a little bit different than what I've done before. Before in the previous slide, I did plus 1 here. And now I don't do plus 1. Just 2 different kernels. And if you do the algebra, in fact, I'm going to comment on it later, you'll see that it results in somewhat different things, but conceptually, it's a very similar kernel. So let's do the math here. So you do this square, you get x1, z1 all square, x2, z2 all square, plus this mixed term. And I can now decompose it to a dot product of 2 vectors. It's this vector, 3 coordinates, x1 square, x1, x2 with square root of 2, x2 square, dot product with the same thing with z. And hopefully you see that this dot product gives it. So what have I shown? I've shown that it's a kernel because I can take this k that you liked and I wrote it as a dot product. It's a dot product in a higher dimensional space. In this case, you just move from 2 to 3. But in general, you're going to move, in the case of quadratic, from n to about n squared. So it's a legitimate kernel. Now, and this is the picture that you should have in mind, right? So you want to be able to linearly separate the blue from the green. You need to work in a quadratic space. Okay? So this solves this problem, the green and blue problem. Is that clear? Now, some of the features may have coefficient 0 if it's really centered in the middle and symmetric, this green thing here. But that's fine. You'll put 0 on these mixed things, and you'll put the same weights on the other features. But that's part of what your learning algorithm will do. Expressivity-wise, we solve the problem. Okay, so the truth is that it's not necessary to explicitly show the feature function phi. So what I said before is if you want to use a function, you first need to show me that you can write it as a dot product in some space. The truth is that you don't really need to do it. There is a more general condition. You have to construct a Graham matrix, which I'll define next, check that it satisfies some property. If it does, then it's going to be OK. You don't really need to show the dot product. What do I mean by that? So Graham matrix is basically the following matrix. Given a set of vectors, it's the matrix that contains in the ij place the dot product of xi and xj. Okay? Notice that this kernel matrix doesn't care about the dimensionality of your data. It cares about the number of examples you have, right? This is what we are doing now, right? So we are moving from representations that care about the dimensionality of the data and require a lot of weights as a function of it, to representation that care about how many examples you have. And this is what this does, right? So now you have two options to think about this kernel trick. Either the direct option, if you have this phi, you have the Gaussian matrix. And it's also easy to see that this matrix is going to be positive semi-definite. The indirect, I realized that I didn't define what's positive semi-definite for those of you, the two of you that don't remember. So it will be in the next slide. And you have an indirect way. If you have a kernel, you say, I want to use this kernel. You can write this matrix, right? It's the Kij is going to be the Gij here. Show that it's legitimate. Show that it's positive definite. And even if you don't know how to decompose it to a dot product in some phi space, it's going to be OK. You can do it. So what do I mean here? So basically, I said that this function is a positive definite kernel if this matrix is positive definite. This is the definition of positive definite. It basically says that for every non-zero z, ZA, Z transpose is positive. So basically what this theorem says is that if the matrix, once you invented the kernel, you know how to compute the matrix. If this matrix is positive semi-definite, then there exists a phi such that this matrix corresponds to the dot product, but we don't necessarily have to know how to compute it explicitly. So essentially, it corresponds to some higher dimensional transformation of the data, even if we don't know how to write this explicitly. OK, so I want to go over a few more examples. I already did these two examples, right? OK, so this is just the no kernel option that we call a linear kernel, just dot product between the original vectors x and z. Second option, a polynomial kernel of degree d. Third option, another polynomial kernel of degree t. Because I added a constant here, you're going to get everything up to degree d also. And you can decide which one you like. OK, so these are three kernels. But in fact, once you have kernels, or these three kernels, you have a very, very large number of things that you can do. Because you can combine kernels different ways and invent new kernels. And in all these cases, you can actually prove to yourself that that works. So the scheme to proving this is going to be the following. For example, I'm saying here that multiplying a kernel by a constant is also a kernel. So you could argue as follows. You could say, let's assume that K is a kernel, which means there exists phi such that I can write K of x comma x prime as a dot product between phi of x and phi of x prime. Given that, you can find also a dot product or a transformation phi prime that corresponds to this new kernel, right? It's clear that this scheme should work, right? And in fact, it would work in all these cases. So let's just think about it. So multiplying by a constant. I lost this. So multiplying by some other function of x and x prime. Applying a polynomial to this. So I have a polynomial, one-dimensional polynomial here, and I'm basically applying it on the kernel. I get another kernel. Exponentiating. All these would work. Moreover, if you have two kernels, you can also use them to generate additional kernels, adding them, multiplying them, and a few other functions. So if you have a mapping, a transformation to another dimension, you can take the kernel instead of x and x prime of the transformed x and the transformed x prime. And again, all these are going to be easy to prove once you start with the assumption or with the definition of what does it mean for K to be a kernel. Okay? So we gave you a huge number of options for how to transform your original feature space to a larger feature space. Here is another one that is somewhat different than the previous one. So the previous one were all discrete kernels. So I had an n-dimensional space, and I moved to some function of n-dimensional space. This is a little bit different. So it's a Gaussian kernel. This is how it works. So it's e to the minus x minus z to some power. I can put sigma in a power here, so I call it c. So basically, you know Gaussians. So if this number here, c, is very, very small, you essentially get x to the x minus z to the 0. You get the identity. Otherwise, you get the unit matrix. And you can also see that basically what you get is something like this. X equals z is in the center. And you want to basically emphasize the cases where x is equal to z and gracefully, as a function of the constant, degrade as x becomes distinct from z. That's the idea. Is it a kernel? Right? So we can ask the same question. And you have the tools now to show that it's a kernel using basically the algebra that I showed before. Right? So what do you have to do? You have to show that either it's a direct dot product of some transformation or some function of this. And it's not difficult to show. So this is k of x, the way I defined it. I'm going to blow this up here, just the square. Now this is e to this power. So I write it as the product of e of something, e to this power and e to this power. And now I have e to xz divided by a constant times some functions, the same function of x and of z, which, if you remember 2 slides ago, was one of my options for how to generate a kernel. So if this guy is a kernel, then k of x is a kernel. And clearly, this is a kernel because x dot product z is just a linear kernel. Dividing by a constant is OK. And exponentiating something is OK. OK? So we proved that this function is a kernel using the previous 2 slides, simple functions of, in fact, the linear kernel. One other interesting, so questions about this? So far, all we did is basically simple things. I didn't prove anything, but all these, well, I did prove it here. I didn't prove the transformation, but all of them are very simple and direct proofs directly from the definition. One important distinction here is that, as I said last time, and I'm going to say in the next few minutes again, everything about the kernel trick is a representational trick, right? Because I showed you that I start with the perceptron over the Ti space, very, very long perceptron with 3 to the n weights, and I just do some algebra and I write it in the example space. potentially shorter representation, depending on how many examples you have. So all this is just algebra. So when you learn, you get the same function. Not exactly the case with Gaussians, where, so basically, what does that mean? It means that if you work with discrete kernels, you have two options. You either blow up the feature space explicitly, or you use the kernel trick. You have these two options, and they are equivalent in terms of what you will get at the end. They are not equivalent in terms of computation or convenience, but they are equivalent in terms of your results. This is not the case because really it's an infinite dimensional kernel, and it's not easy to show that you can actually write it down explicitly as dot products. So this, in principle, gives you something. Now, there is a little bit of kind of cheating in what I'm saying here, because really you can say the gram matrix is finite, right? It really depends on how many examples you have, right? So what does it mean, infinite dimensional space? It's n by n matrix. So in principle, you could say, maybe I can take this gram matrix and numerically or some other tricks find an equivalent representation as dot products of some vectors. And this is, in fact, a question of active research where people try to approximate the gram matrix using some dot products so that they can do these things explicitly and sometimes save time. But in principle, this is true. OK, so let me summarize what we've said so far. So basically, we presented it as a way to re-represent perceptron this way, right? So our function of x, instead of being written in the feature space, is now written in the example space. So if I have a very large feature space, I can compute perceptron this way without incurring the cost of keeping a very large weight vector. And again, I said it really pertains to efficiency and not so much to generalization. You'll get the same generalization properties. Now, it's important historically and also in terms of what kind of algorithms you want to use. It's been popularized, let's say, over the last 15, maybe even more years now, by support vector machines that you don't know yet. At least you just got a definition last time from the perspective of a loss function, but you don't know algorithmically what it means. But really, you can apply it in a range of models. So I showed how to apply it on perceptron, right? This is how we define our kernels. But if you like PCAs or Gaussian models or a range of other models, all of them know how to deal with kernels. So instead of features, you can run these algorithms on kernels. You cannot do it for multiplicative update algorithms. We cannot use Wino with kernels. And in fact, we suspect, although we don't know how to prove, that it's impossible. The reason is that so I show that we can run kernel perceptron over 3 to the n monomials, which means any Boolean function over n variables, we can run kernel perceptron and learn, right? Now, the complexity of this is going to be a function of the feature space, 3 to the n, exponential. Because if you remember, we talked a little bit about mistake bounds. Mistake bound of perceptron is the size of your feature space. On the other hand, for Wino, it's actually just logarithmic in the feature space. So if you were able to use kernels for Wino, it's a hand-wavy argument that can be made a little bit more explicit. I'll give some pointer in the next slide, you would actually be able to learn any Boolean function in sub-exponential complexity, which will contradict a lot of complexity theory results and so on. So that's why people think that there are no kernels for multiplicative algorithms. But as I said, it depends on complexity theoretic assumption. Okay, so I want to talk a little bit about this trade-off that is really, really important in practice. You could already imagine that there is a trade-off between computational efficiency here, the size of our feature vector, and generalization ability in general, right? So what can we say about this trade-off in the context of kernels? Let's assume that you think that kernels are good for you for this specific problem. So you're going to use kernel perceptron with your favorite kernels, polynomial of degree 7. But you were wrong. Actually, linear kernels are good enough. You just didn't know your problem well. The question is, does it matter or not? Right? Which is equivalent to the question, should I always work in as expressive feature space as my computation afford or not? And the answer is no, don't do it. Because one can show that if the function was simple, it would have been much better for you to work in the original space. You're going to suffer by blowing up the feature space and working in it. It's going to take you a long time to figure out that the higher level features should have weight 0. Right? And this can be done in a rigorous way. And in the limit, you're going to make exponentially many mistakes because you blew up your feature space. And the second, the last bullet here is actually a very practical bullet that I'm going to give some concrete arguments. So this answers the question that you asked before, which is, what do I do? I know that I have m examples. I know that my original space was of size T1. And I'm considering blowing up the feature space to size T2. Should I do it or not? Right, that's a practical question. So, so let's think about, if you were to work in the dual space, what are the operations that you're going to do? So each operation that you will do will be in the original space, dimensionality T1. And for all pairs of examples, you'll have to do something. Right? Because f of x is computing something for x and all the other examples. And you want to do it for all x's, so it's quadratic. So basically, in the dual space, this will be sort of the rough complexity of what you will do. In the primal space, your dimensionality is going to be T2. But essentially, you're going to do it once for every example. Right? You'll have weight, and you'll compute the weight vector. So now you can see, you know, if T1 is much, much smaller than T2, it really boils down to the number of examples. If the number of examples is much larger than the ratio of T1 over T2, or T2 over T1, then this m square is going to cause you to suffer. So it's a very simple simple trade-off. And in fact, I'm going to get to it with some concrete example at the end. In many applications today, when people, for example, in the natural language processing domain, where people work over complex structures and therefore they think that they need expressive features, in many cases, you will see that people write or describe their algorithms or their methods using kernels. And the reason they do it is because it's easy to think about it this way. But in practice, what they do is they blow up the feature space. So they talk about the kernel to explain what kind of features they're going to work with. But computationally, they don't use kernels because they don't want to work in the dual space. They want to work in the primal space. So they explicitly generate the feature vectors. I'll give an example of where you can do something like this. Questions on this? Okay, so that's a good. I'm cheating a little bit, right? So I said M, and I didn't say what M's. What are the examples? So if you do perceptron, it's true that M is only the number of examples you made mistakes on. If you do SVM, in fact, it's all examples. But even there, you can say, okay, it's only those examples that we care about. These will be eventually called the support vectors. Those examples that are close enough to the line and really determine the line. If examples are very far from the line, no one cares about them. So it's never really all the examples. But let's assume here, for the sake of, waving our hands, that it's linearly proportional to the set of all examples. So let's say you're making mistakes on 10% of your examples. So still, order of magnitude here is correct. In fact, the real bounds that people can prove are even worse than that. They're going to be, here they're going to be cubic, not quadratic. But in real life, I think it's a lot more close to quadratic. Okay, so we talked about a trade-off of efficiency. You can also think about generalization, right? So let's assume I can afford it. And I'm not sure exactly, should I blow up my feature space or not? Are you going to lose from just blowing up your feature space via kernels or explicitly just because you can? What's the intuition? What do you think? I mean, you have a problem in an n-dimensional space. If all you need are these features, say, but you decide, just to be on the safe side, to add all the quadratic and the cubic terms also. Will it help? Will you suffer? It must be that you suffer from it. Right, so basically, you will suffer in terms of the generalization, right? So if you think about it, it will take you time to decay the weights, or equivalently, if you stop at the same time you would have stopped with the smaller dimensional space, you will not generalize as well. So, and again, we can develop a simple argument to kind of show that this is the case. So let's go over this argument. So you're given a linearly separable set of points, n-dimensional points, and I want to embed it into a higher dimensional space. N prime is going to be greater than n. So in this simple exercise, the way I'm going to embed it is I'm just going to add random features, but I'm not going to hurt you. I'm going to add zero mean random noise E in all the additional dimensions. So really, it doesn't matter, as we will see. So now, why doesn't it matter? So my new feature vector is going to be W prime, which is really W, and I add zeros for all the irrelevant features that I've added. So the weight of all the irrelevant features is 0, which means that W prime X, which is W concatenated with many zeros, dot product with X concatenated with a lot of noise, is the same as WX. Okay? So now I have a new weight vector, but it still separates the data. Right? If this separated the data, then this separates the data. They're the same. So now let's look at the margin. Or in fact, I'm looking at it, the margin divided by the size of the example, which we've shown for the perceptron to be the important complexity parameter. It tells us how many mistakes we're going to make. Right? The larger the margin, the better we are. Right? The larger the margin means that the problem is easier. Right? The examples are farther away from the linear separator. It's easier to learn. Smaller the margin, you're going to work harder to fit this linear separator there. So let's compute this thing. So I'm going to compute the gamma of S, my set of examples, with this new vector, weight vector, divided by the size of this new example. Really, this margin is the minimum over all my data sets of this thing, right? So W prime transpose X transpose, normalized, divided by W transform, and then dividing by X prime, sorry. What can I say about this? This is exactly as W transpose X. I showed that these two are the same. I showed that these two are the same, W prime W, the size. And I'm leaving this X prime here. But because the size of X prime is greater than the size of X, I'm going to suffer here. So my margin in the new space is going to be smaller than the margin in the old space, which means I'm likely to make more mistakes before I'm likely to take more time before I manage to learn something. Okay, so I really gave you here a very concrete and simple scenario, not the general case. I added noise, but just I wanted to give the intuition that just blowing up the feature space where it's not needed is not going to do any good, right? Which hopefully matches your intuition. Okay, so basically we talked about kernels so far from two perspectives. The trade-offs, right? So on one hand, in the second argument, we said, don't just blow up your feature space if you're not sure that you need it. And in practice, what you will do when you work on a machine learning problem, you will start with your original space or something that you're sure you need. If you see that you cannot feed the data, that's why I suggested every time to look at how well you're doing also on the training data. This will give you an idea of your expressivity, right? If you know how you do on your training data, you know how expressive your model is relative to the data. And only if you need to, expand your feature space. And the second thing that we said earlier was this issue of complexity that tells you, should I work in the primal or should I work in dual? And that's, again, an important consideration. So, okay, so let's conclude this part. We talked about kernel. The notion of kernel is very, very important for two reasons. First of all, because it allows us to think about the dual space. And second of all, it really allows you to think about your problem and the features needed for the problem in a more reasonable way sometimes. You really think about, I have elements in my domain. How do I want to think about their distance? How do I want to define their distance? As an example, let me give, I'm not going to have time to go over all the details, but I want to give an example that is for structured data. So let's assume the data that you have is text. And when you want to think about the distance between sentences, rather than staying in the word space that you see, you want to think about the distance between sentences as the distance between the parse trees of the sentences. you can imagine some other functions. It doesn't have to be the parse tree. It could be some kind of an HMM, right? So think about this as some sequential analysis of the test. It could be parse-speech tags, or it could be some other type. Maybe this is an entity, this is not an entity. Or this is a person, this is a location, this is an organization. So some sequential analysis of the sentence. We can keep the parse tree as an example because I'm going to continue with it. But you can imagine that this makes sense sometimes, right? So I have domain elements, and really thinking about dot product between domain elements is nothing but thinking about the distance between domain elements. So I want to think about parse trees rather than just the word sequences. If that's what I want to do, I need to define kernels over them. And the way people thought about this is, let's think about defining kernels. The way I'm going to define the kernels, I'm going to skip here some things. You can go over it yourself. What I'm going to do is I'm going to consider all the subtrees of a tree as my components of the vector. Right? So think about a parse tree, a tree. And then how do I represent this tree? I'm representing it as a vector where the coordinates of these vectors are all the subtrees. We define a way to enumerate all the subtrees, and now I have a vector. So my dot product now becomes dot product between all possible subtrees, where it's really a binary. It could be a binary representation. Does this tree have this subtree? Or it could be a real valued representation. How many times does this tree have this subtree? Okay, this is what's written here. So I can invent the following feature. Given a tree, how many times does it have this in it? But I can also just define a Boolean thing, does it have it or not? And depending on the application, you may choose to do different things. So at the end, what you will get is you will get that what you need to do, this is going to be your representation, huge dimensional space, right? But it really has some semantics, right? Now you're measuring the distance between sentences as the distance between the parse trees of the sentences. So this is going to be your dot product. So you can run kernel perceptron with this as your dot product. What's going to be the kernel trick here? The kernel trick is going to be, is it possible for me to look at the two trees, not computing all the subtrees, and figuring out what's the value of this dot product is? Is that clear? So it's the same exercise we had before, right? We start with x and y, x and z. We are not happy with the representation that we're given because it's not expressive enough. We want to transform it to a high dimensional space. And because we're familiar with the structure in our domain, in this case it's sentences, parse tree makes sense, we use this as a way to generate a very high level representation of the same data. Right? And in this case, as I said, this is going to be all the subtrees. We can just do this explicitly, right? And compute dot product. Everything is going to be fine. Or we can use the kernel trick. In order to do it, we actually have to develop an algorithm to compute this huge dot product efficiently. So now we can talk about the two issues that we mentioned before. First of all, computation. It turns out that you can do it. So I'm not going to go into the details because I want to at least hint on another thing that we're going to talk about still today. But you can go over the details and see that there is a dynamic programming algorithm that if you're interested, you can try to understand. I think it's relatively straightforward, that allows you to compute it. So the computation part is done. There exists a kernel trick. for this. And in fact, this is true for a lot of structures. The same principles that apply here can be applied for a lot of structures. So if you are familiar with the structure in your domain, you can use these ideas. The second question is, do I want to do it? And the answer to this turns out to be no. You don't really want to do it. It's very elegant. You know, the dynamic programming algorithm is cool, but you don't want to do it. And the reason you don't want to do it is because if you take all your subtrees, right, huge set of subtrees, most of them really are not important, right? Because think about it. Large subtrees are not going to be repeated in different sentences. So these are going to be features that you hardly see, but you still carry them with you. So it's very similar to this caricature scenario that I had, where you just blow up your feature space because you can, but you get a huge number of features that are not important. So what really happens in this case is that you really want to generate just a small number of small subtrees, which is equivalent to using this kernel and putting zeros or very small numbers next to all the large subtrees. Right? This is what eventually your learner will do. So again, you can use this example in several ways, right? So one, it shows you that conceptually kernels are interesting, right? Because really they allow you to think about your problem from in an interesting way, right? Think about really what's important in the structure. What you do with it later, you can take two routes. You can either compute the kernel and use it, or you can say, you know what, I'm actually going to generate explicitly the representation because this gives me a lot more flexibility. For example, I'm going to get rid of all the large trees, just keep a few trees, and I have a much smaller representation, but it's sufficient. So this is a trade-off that people do a lot in practice. Okay. And by the way, you can do the same thing with polynomial kernels, right? So if you have n features and you want to move, you think that some quadratic terms are important. For example, in the context of sentences, you care about trigrams, which are consecutive words. So you don't want all the quadratic terms. You just want or cubic terms. You just want cubic terms that are correspond to consecutive things. You can do this explicitly. Only linearly many things are going to appear, rather than cubic if you really believe the cubic kernel. So these are practical things that, again, you draw some insight from the kernels, and then you do what you want for your problem. Yeah?
So in both the examples that you mentioned,
Large trees.
large or
Yeah.
or three of
It's exactly it's the key problem in machine learning. What are the features, right? It's the same problem, right? So we don't know, we don't have a theory for inventing good features. We know that we need good features. But this is a good segue to what I wanted to talk about next, and I see that I will not finish it, but at least it will I'll give you some idea of where we're going. In fact, this is going to be the last lecture on online learning. But what we did so far is we talked about features, right? So everything I've done today was talking about what features are good if I know that my learning machine is a linear learning machine. And it's not sufficient. So I need to change the input. Right? That's basically what we did. We said, I have a learning machine, could be perceptron, could be any gradient descent algorithm, could be Winnow, could be later SVM, but it's a linear machine. the features are not expressive enough, so we are blowing up the dimensionality by changing the features, and now we can use a linear machine. So that's not the only solution. Another solution, okay, so this is just to remind myself that that's what we're talking about, right? We're talking about moving from an unsolvable problem using linear machines to a solvable problem. That's what we did. But it's not the only solution. So the other solution is to say, okay, let's change the machine. Let's not work with a linear machine anymore. This way, keep the feature as they are, and let the learning machine do something, and eventually we'll get something more expressive. In fact, with decision trees, you kind of got something like this. And neural networks, or multi-layer perceptrons, as they're sometimes called, also give you the same kind of thing. So for historical reason, I have to say that I think until 2004 or 5 or something like this, I used to teach this. And then I stopped teaching it because while it's an important algorithm, the one I'll get to, there's a lot of issues, theoretical issues and practical issues with its importance. As many of you know, the last 2 years or so, people changed the name from neural network to deep networks, and suddenly it's much more successful. There are a few other technical reasons for it, but really no algorithmic reasons. Mostly architecture became much better, and we have a lot more data. So we can run these networks on really huge amounts of data, and we have much better machines, GPUs, and so on, so you can actually do more things. It's not clear if, well, it's clear that nothing significant else has changed, but you can do things that you couldn't do before with this network, so it becomes more interesting, so I'm going to talk about it. So what is it? So basically, it's the idea is the same idea as earlier in the lecture, to overcome the computational limitations or the expressivity limitation of linear networks. So what we're going to do is we're going to stack several layers of threshold elements, where the idea is that the output of this threshold element is going to serve as input to the next threshold element, and so on. So what I'm showing here is a 3-layer neural network, but you can imagine cutting here and putting more layers. In principle, it's going to be the same. It turns out that expressivity-wise, 3-layer neural network is sufficient. Any Boolean function, or in fact any real-valued function that you want to represent, you can represent already with 3-layer neural network. Theoretically, we don't know why these things work, because in principle, it shouldn't converge. There are some interesting theoretical questions there. And computationally, also, these polynomials are all NP-hard once you define them properly. But what can we say? So, OK, so first of all, just to understand what these networks mean. So if I were to put a linear unit in each one of these places, so every time you have a node and all the wires that go into it, if it was a linear unit, we've done nothing, right? Because if you chain linear units, you get a linear thing. So we don't want to chain linear units. Instead, what we're going to do is we're going to chain threshold units. So at every internal node, I'm going to apply these threshold elements, sign, and then send the activation value to the next layer. Now I've done something that is nonlinear, so it makes more sense. The question, of course, is what can we do with it? And if it's just a threshold unit, there's nothing you can do because it's not continuous. So the key observation came about 30 years ago, and in fact, it was known probably about 40 or so years ago, definitely in the 70s. And in fact, everything I'm going to talk about was popularized in '86 in a collection of books that you can still find very useful called PDP. I don't remember what PDP stands for, but if you Google it, you'll... Again? Parallel distributed processing. So there's a sequence of 3 books, I think, by these people and a few others. But really all the ideas, including the learning algorithm, was known at least in the 70s. But basically the key observation is this. We can replace this threshold element with a continuous function. For example, one way to do it is to take this logistic function that we've mentioned before, 1 over, I'm writing it here as to the power of -1 because I can't write 1 over, e plus 1 plus e to the negative of the dot product. This, with a little bit of constant here, can be made as close as you want to a sine function, but it's differentiable. So we're going to replace the units by these units. So this is actually what we are doing, right? So we have this perceptron that I showed before, and instead of a step function, if you go back a few lectures ago, you'll see that I put a step function here. I'm replacing it by a smooth function, which is this function. Now, here I'm writing it with a threshold element. In the previous slide, I wrote it without a threshold element. You know that it's the same and it doesn't matter, so it shouldn't bother you. You'll see it different ways in different places. Okay, so what are we going to do? So I'm not going to do the math today. I'm just going to give you the hand-wavy argument. So the idea is that we still want to learn. But how do we learn? So it's very easy at the top, right? Because at the top, you get some inputs. They came from the bottom, but it doesn't matter now how they came. And you have feedback here. So you can just use perceptron, right? You have feedback, you have some input, learn. Update the weights that I denote here as Wij second layer. We can learn them. You can use perceptron, gradient descent, do whatever algorithm you like. The problem is, what do I do here? Now, no one gave me feedback for these intermediate nodes. So I cannot run perceptron. I cannot run a standard linear learning algorithm, right? So this is the challenge here. How to train the weights in lower levels, given that no one gave me feedback. So the trick is the following trick, right? The solution is that we say if, essentially we can think about all the activation functions, because the change I've made, all of them are differentiable. And therefore, the total activation of the network, the output of the network, is also a differentiable function of the weights and the inputs, right? So now I can define an error function, just like we defined when we did, least mean square. And this error function is going to be differentiable as a function of the output, and therefore differentiable as a function of the weights, because the output is differentiable as a function of the weights. Given that, I can use essentially gradient descent, or in general, I can just compute the derivatives of the error with respect to these weights, all the weights now, use these derivatives to find better values for the weights, those that minimize the error. And once I know how to do it, the question is only, which optimization rule to use. But we've already talked about gradient descent. I can use gradient descent as a way to change the weights so that they lead me to a smaller error value. So I'm not going to do the math here. I'm going to do it at the beginning of next time. It's actually a very simple thing, if you think about it. It's a slight generalization of what we've done before with gradient descent, only that I have to tell you how to do it for each layer. But really, it's the same principle of differentiating and backpropagating the error. And this is why this algorithm is called backpropagation. Was the question? what you did with the cascade, with the decision trees and then stochastic gradient descent. Yes, but you trained them separately. That's the key difference. So I gave you feedback for the intermediate level. This was when you trained the decision trees. And then you fix that, and then you train the stochastic gradient descent. That's the difference. Here, I'm not going to give you feedback in the intermediate level, just at the top. And the question is, can you propagate the error so that you can update your weights by itself? That's a very good sort of analogy. Or we'll talk about it next week. Okay.
Question about multilayer. So is there any way of knowing how many hidden layer perceptrons that you need, or
how many? How to construct? Sorry, the hidden layer, basically.
Yeah.
So it's